so this is the ninth lecture in its series. So I welcome you all. So the main motive behind this society was to bring all the stakeholders, including academicians, researchers, industry organizations who are working in the field of structural health monitoring at one platform, so that they can all interact with each other. They can leverage the expertise of each other, because see, in India no such body was existing as such. So the idea is to take structural health monitoring to the next level, to another height, so that we can because there are always some kind of confusions many a time. So we are producing some kind of guidelines also in structural health monitoring. So these are all the motives of structural health monitoring society, so that this can be taken forward. And so I'll formally welcome our speaker, Dr. Saravanan, first of all, and I will introduce our speaker. So Dr. Saravanan is currently serving as the assistant professor in the Department of Civil Engineering at IIT Bhubaneswar. His major research interests include structural health monitoring, structural dynamics, smart materials and structures, system identification, vibration monitoring, machine learning, deep learning, computer vision, image processing. He previously worked as JSPS postdoctoral fellow at the Institute of Advanced Sciences, Yokohama National University in Japan. He was a visiting scholar at the University of Cambridge, UK in 2016, and was honored with the Promising Young Structural Engineer Award by the ISHMS National Awards. We welcome you, Dr. Saravanan, and thank you very much for joining us today for this lecture series.
Yeah,
We
thank you,
are
madam.
looking forward to hear from you. So he'll be giving his talk on advanced computer vision technique for structural health monitoring. Over to you.
Yeah, thank you. So first of all, very good evening to everyone. So a big thanks to Professor Balla, Professor Vishalakshan, and Dr. Navid Kaur. Today, we are going to touch upon some advancement and also for some future design, health monitoring for current state estimate. Okay, so what is the current scenario of my structure? And deterioration monitoring. So what will be my future performance prediction and optimum maintenance strategy? So these are all some of the typical points as a structural health monitoring expert we should keep in our mind. So I think this slide is just giving you a brief introduction or the preamble for the state of the art damage detection, which was primarily remains with visual inspection, and of course it has been replaced with local non-destructive evaluation. So you can see that it is not only for civil engineering, but right from the aerospace engineering, wind turbine, and underground structures, okay, or like bridge structures. So the first point is our visual inspection. So then we try to do some local NDE. Then of course, we try to mount sensors for long-term evaluation of particular structure. So this is something very important thing where I want to emphasize that though we have a lot of advanced technologies, visual inspection is something we don't have any replacement for that. So I want to comment that there is no sensor that can measure damage. So we should understand this. So there is no sensor in this world that is going to measure you a damage. It is just going to measure the response of a system to some stimulus. So you are going to give some input, there is some output. So that output need to be integrated. Okay, so you need to have some data interrogation procedures to develop some effective solutions. Okay, so that's what we're going to do. And for doing this, there are a lot of advancement in this area. For past two decades, health monitoring is getting peak, and currently computer vision technique, maybe I can say after 2015. So when the first paper got released from MIT thing, so for the computer vision based health monitoring, so this has become the talk of the town now, where almost all the researchers are trying to touch upon this computer vision part. So this slide is just trying to tell us what are the different types of loading my civil structures is going to take place. Because of that, there will be different levels of severity, damage severity. So health monitoring, as we all know, it is going to play a vital role in identifying and mitigating the potential structural damages. So now, so there are some traditional sensors. So when we talk about sensors, there are some traditional sensors. Now I am going to like classify this sensor into two types. First one is called as contact method. Okay. So where what do you mean by contact method? You try to mount the sensor onto my structure. Okay. That is something called as contact, where your sensor is trying to be attached to the structure. Let us say like strain gauge, temperature sensor, accelerometer. Okay. So where ultimately these are like coming under the traditional measurement. So you try to measure the vibration characteristic of the structure. That's the basic understanding we all have. Okay. So there was some like problem when you go with some sensors, like when you mount some heavy sensors to the structure, that is changing its dynamic characteristics of that particular structure. If it is like lightweight, that is one point. And also it is very tedious for us to go there, reach out there and like mount a sensor and again go and like look into it. If it is like a long term monitoring, for example, let us say like 3 months, 6 months, or 8 months, or 1 year, so these sensors need to be taken care in the periodic maintenance need to be done. Let us say that we need to change the batteries, we need to like check for the connections, we need to check for the nodes, we need to check for the whether the response that is collected is being like transferred from one node to the another. For example, like when I was in Japan doing my PhD, so I can tell you like small experience where like we try to do the condition assessment for bridges there. So we as a team from Tokyo University, we go to the site, we mount the sensors. Every 3 months, we go again to the same site to change the batteries for it. So while we do that, it is not only the job to change the battery, but also we try to check whether the it is something like wireless sensor. So we need to check from one node to the another whether there is a data transfer. Okay, we used multi-hop technique. So whether the data is like captured from one node to the another, and at the end whether the sync node is trying to get the capture the data. So these are all some of the difficulties which we faced. Okay, so installation itself is like big problem that we all are having, and like we are trying to like overcome these things. Okay, and it particularly depends upon the site condition. So now these are all coming under the category of this contact sensor based. So now how to like think alternative for this? So there is something called as non-contact. So where I'm not going to touch my structure, but I'm just going to measure the response of it. Okay, so that is really cool. But the problem here is there are like several non-contact sensors that is available, particularly which is like having this laser based equipments, which is like very expensive. So laser doppler scanning vibrometer is one of the robust equipment which is going to give you the response of your structure. Let us say displacement or like wave mechanics or anything that you want. Okay, and it depends upon right from the normal composite structures to the bridge structures. You can use those equipment, and it is going to give you really a very good accurate results. But the problem is it is like high cost. Okay, so the requirement for do this, you need to have some better skill. So to do this, like there is a requirement for some alternative non-contact type of sensors. So there comes this camera, so where it is going to just capture the image of my structure, and I'm just going to utilize that data set to understand. So for doing this, like I can use like high resolution cameras or like high speed cameras. So that was the first thing. Then there was a digital image correlation. Then there was something called as like where I can use the 4K resolution normal like DSLR camera, or like nowadays even the smartphone can be utilized to do the measurement. Okay, so that's what we are going to do with. So now if I'm going to take a video of my structure, how am I going to use my existing computer vision technique and the machine learning techniques to understand it? So the today's talk will be more or less focusing on this, which is something like an unsupervised learning algorithm for computer vision based blind model parameter identification of output only structures from video measurement. So let me just break down this. So we're just going to use something called as unsupervised machine learning. So under machine learning, there are like two categories. So which is like supervised and unsupervised. And there is one more parallel thing which is called as the reinforcement learning. So, okay. So unsupervised means we are not going to train the model with the proper input. Okay. But it is going to be it is going to extract, okay, from the unsupervised part. So it is going to extract from the data set which is like not trained. Okay. So now this unsupervised machine learning algorithm is going to be sit over this computer vision part. Okay. So where we are going to use some capture. Okay. We are going to capture some images or videos. So particularly this methodology is done for the blind model parameter identification. So if you could understand what is operation mode analysis, so which is something like under mode analysis, there are like two categories. One is operation mode analysis, another one is experimental mode analysis. Okay, so in the operation mode analysis, where the input is unknown, we have only output. That means the response of the structure. So from there, how you are going to get your model parameters. The model parameters here, I say particularly the natural frequency, damping ratio, and in some cases mode shapes. Okay, so these things are going to be obtained from output only structures from video measurement. So but before doing this, so we also conducted some part of the research on video motion magnification technique for non-contact operation mode analysis. So this was something like method proposed by MIT professor in 2015. So we tried to implement in 2018, and somehow we achieved it. And we now currently we are working on unsupervised learning, and again like we are also trying to improve this technique. Okay, so why I'm trying to say in the reverse manner, because so to do this method, okay, so we need to understand from this method what is the difficulties we had, uh, what are all the disadvantages we faced to improve that method. Okay, technically that's what I want to say this. Okay, so there is a story behind this, where so this method is having some drawbacks or disadvantages where we are going to overcome that. Okay, that's the ultimate aim of this particular lecture I'm trying to cover up. So now let us try to understand about this video motion magnification. Okay, so where we are going to use for the non-contact based operation mode analysis. So let me just put this slide where like you have like three different classifications. Okay, the first part is for the phase based motion magnification method. Second one is the displacement extraction, and third one is the operation mode analysis by any system magnification method. Okay, so now so let us just understand the story behind this. Okay, so phase-based motion magnification method. So something called as magnification, you can understand motion magnification. That means your motion means vibration. So you're trying to magnify the vibration of my structure. Okay, so how you're going to do using the phase-based method. So when it comes phase, okay, so let me just slightly enter into the methodology. First is the video measurement. So you can just stand in front of your structure, take the video of it. Let us say it can last from 20 seconds to 1 minute or 1 hour. It depends upon the computational efficiency. Okay, so first you take the video measurement. It can be from your DLSR camera or like high speed cam, or you can also use your smartphone, not an issue. So next you try to do some two-dimensional Fourier transform, and you're trying to perform certain types of filtering here. So when you do Fourier transform, as we all know, so this video measurement is something like in pixel coordinate. Okay, so when it is a video, it has like number of frames. When the number of frames, I hope you understand what is FPS, like frames per second. Okay, so when you have number of frames, so you need to like separate the video into number of frames, n number of frames for example. Then you need to analyze one particular frame which is having x, y. Okay, f of x comma y, which is something like trying to talk about your pixel coordinate. So now since this is like two-dimensional, I'm trying to perform two-dimensional Fourier transform. Okay, so when you perform Fourier transform, you have amplitude and phase part. So I'm more interested in the phase part, not in the amplitude, because phase part is going to have the motion characteristic. That's the reason this method is something called as phase-based motion magnification. Okay, so once you do that decomposition, okay, once you separate the frames from frames, you try to get the amplitude and phase. Again, you try to implement some filtering part. So here filtering means I'm trying to do the normal bandpass filtering. I'm going to fix some range of frequencies. Okay, so please remember this point. So this bandpass filtering, which I will be again touching upon after we complete this methodology. Okay, so here bandpass filtering means you need to fix your low pass and high pass filter. You need to know that value. Okay, then once you do this, then you try to do the image decomposition. So technically we use complex steerable pyramid. It's one of the method where you try to have multi-scale image decomposition. So at each level, at each frequency of that particular image frame, you try to like extract what is that one thing which is trying to like uh, have that motion characteristic, or which is going to participate in my motion matrix. Okay, so once you do this multi-scale decomposition, you try to go with the phase magnification of each frame, because you have like separated frames. Then you try to magnify that frame with some alpha factor. It can be 10 times, 100 times, or 1000 times. So now your frames are magnified, technically magnified in the sense your phase information is magnified. It's not you're trying to zoom thing. Okay, it's not like that, but you try to magnify the face of that particular frame. Once you do it, then you try to implement some tracking algorithm, which is proposed by one of the famous Japanese professor Otsu. So his algorithm is something trying to help us to extract the displacement part. Okay, so we try to convert that frame into 2D grayscale image. Okay, before we have in RGB, then we try to change into grayscale. Then we convert that image or the image frame into binary image. So when it comes to binary conversion, it is 0 or 1. So wherever it is 0, there is no structure. Wherever it is 1, my structure is present. So wherever it is going to show 1, that matrix part is going to be analyzed. Okay, from there you're going to establish some threshold value, which is called as Otsu threshold. Then you're going to compute the centroid of that particular irregular frame, then extract the time history of that centroid. So once you get the time history, this time history is something like very much random in nature. So to extract the model parts, or if you want to handle something like random signature, there are like a lot of like system identification techniques. One of the robust or like well known technique is like random decrement method, which is like implemented just to obtain the free decay signal. Once you get the free decay signal, it is easy for us to implement the logarithmic decrement algorithm to get the model damping ratio. Similarly, once you from that free decay signal, you can like do the FFT part and get the model frequency. So this is the rough methodology, like what we're going to see. But I'm going to like repeat this methodology with a lot of examples where you can again get back the steps. So I'm not going to go deep into the mathematics, but I just want everyone to understand what is the steps or the story behind this so that you can appreciate the method. So I think this is something like theory behind it. So you can see I of x plus del x comma t. So this is something like intensity, which is representing the image intensity. Okay. So where x comma t is something like representing both spatial and temporal coordinate. Okay. So as time changes, how your particular pixel is going to change. So that pixel is need to be tracked down, and you're going to extract the information from that. That's what we're going to do. For doing that, I think, as I mentioned, we're going to do two-dimensional Fourier transform, and we're going to it is extracted by the multi-scale and localized filter, particularly bandpass filter. Then you implement Otsu method for displacement extraction. Then you have the model parameters from the displacement response, where you implement both random decrement method and the logarithmic decrement technique. Okay, so this is the flow behind the proposed method. So this was the very simple experiment which we have conducted. So you can see 2 degree of freedom system shear building, which is made up of aluminum and like material. It is something like kept on the uniaxial shake table. It is going to like move only in this direction, x direction, and you have a well-known like a camera. Okay, 4K resolution, a video cam. We have just Sony cam we have kept just to record what is happening here. Okay, so to check what we are going to obtain, we are also mounted some white color. I hope you can see Note 2, Note 3, and Note 4. They are nothing but the wireless sensors. Okay, and of course, like we have the sync node which is attached to the laptop. So from here, the data is getting transferred. That is like IoT based experiment where we are just trying to transfer the data remotely. Okay, wireless sensors. So now from these sensors, we can easily extract the model parameters because it's recording the acceleration, and we can like extract the model parameters from there. So these model parameters need to be checked from the video camera measurement. That's what we're going to do. So this is the plot that is obtained from the accelerometer, which is like wireless sensor. So where you can see a very neat plot is obtained. Okay, so which is like free decay. It's something like a free vibration. You just try to tap the frame, so it is trying to vibrate and it is trying to come to the uh, rest position. Okay, so you can clearly see how it is trying to die down. Okay, so Note 3 and Note 4. From there, you try to get the Fourier amplitude, where you can clearly see there is a peak at 1.855 hertz, which is nothing but the first natural frequency of my structure. And there are like slightly other peaks, which is at 6 hertz. Okay, so try to remember these two values. So now, using that video, we are going to extract these things, these informations. How to do that? That's what we're going to do. So I have taken a video. So now my video is going to have something like around 570 frames or like more than this. I'm just randomly picking one frame. This is one frame. Okay, this is the still frame of magnified motion. So here I'm trying to implement all the methods which I mentioned prior. First try to extract the face, magnify the face. Like for example, here we did 100 times. Then we try to like change that RGB to the grayscale. Okay, I hope you can see it's like in grayscale image. Then you try to change from grayscale to the binary. So from here you could able to extract the displacement. Okay, so this is something like, you just see the subplot here. Okay, the displacement extracted from video motion magnification. So you can see that it is quite random. Okay, which is not at all like good to see. So now I'm trying to implement the system identification technique, which is random decrement signature, just to obtain the free decay of this. Okay, so I'm just obtaining the free decay of it. So once I obtain this, it's quite simple for me to get the FFT of it and get the natural frequency and the damping ratio. So which is like 1.855 hertz. And again, similarly, I'm doing the similar pattern for the second hertz. But the point here is, so here, let me just go one slide back, or like let me stay here. So if you see the first plot, displacement extraction, so here you can see only one frequency that is magnified, that is 1.855. The second frequency at 6 hertz is missing. Why? Because in this method, as I mentioned earlier, the band pass filter has been fixed such that range of like 1.5 to 2 hertz. So only in between that we could able to like extract. Someone can ask, why can't I fix from 0 to 10 hertz? Yes, you can fix it, but the problem is there might be like a lot of other peaks, like minor frequency peaks, which will like disturb the major dominating frequency. So that's the reason we try to fix that band pass filtering in a very small range if you have some knowledge onto a structure. Okay, similarly for this we have fixed something around like 5.75 to 6.5 hertz, so where you could able to clearly extract at 6 hertz. So this method is reasonably working very well. So then like we try to implement on cantilever beam. So here like you can see a very simple cantilever beam where we are having a video record, and also like to take the reference of it, I'm not mounting any sensors to it because it's like very lightweight structure, which the sensor mass is going to like influence the frequency value. That's the reason like we go with the laser Doppler vibrometer, which is like itself a non-contact measurement equipment. So where you just kept in front of the specimen and you just try to measure. But the problem is it's quite costly. And here for video cam, you can just replace with even a smartphone if you have a tripod. So now this is the result from the laser Doppler vibrometer, which is like a very neat result. So there is like clear spike at 2.832 hertz, which is the natural frequency of it. Okay, so this cantilever beam is like having a neat free decay signal. Okay, when it is given free vibration. So this is for the magnified motion. So where you can see here, since my video was not in very high level of like resolution, okay, it's like a normal cam. So where you can able to see there are some lot of noises. Okay, so when you try to magnify it, you could able to appreciate that there are like a lot of noise. Even if there is a noise, this method is trying to help us to extract the things. Okay, that is quite good for us. It is quite efficient. So we try to convert into grayscale, then binary image. From here, we are trying to extract the displacement. You can see like very good displacement has been extracted. From here again, like when we plot the FFT, we could able to get 2.81. Very closely it is matching. The error is like less than 2%, or like it is always less than 5%, which is like quite reasonably good. So now what we did was like, so we want to like implement somewhere in practical, in the real time. So this is something like a Google image of the Kinkocho junction, okay, which is quite famously called as Kinkocho JCT. It is in the Kanagawa prefecture. Okay, it's like near the Yokohama station in Japan. So it is something like the top view. So where you can see it's something like a double decker expressway. You can see there is one path going here, and another path you can see there is a curved expressway bridge here. That is the second one, and there is a straight bridge. Okay, road over bridge where I mean like you can able to like appreciate there are like three components of this bridge, and this particular part of the bridge, okay, that curved one is having double decker. Okay, so where the traffic is going to move in both the lanes, okay, both decks. Yeah, so this is the picture that we have taken. So I hope you can see, right? So there are like, it's a curved one, so where you have like two decks where uh, vehicles pass through, and this bridge is getting connected to the next bridge, and of course in between there are like a lot of shopping complex that is existing, and beside this, or like behind this, there's a big station. Okay, this is something like these are the pictures which I have taken. Okay, so now if you see here, so there are like a lot of light poles. Okay, so there is a Kajima Corporation, which is like a steel company. So they want to understand. There was like particular problem statement we had. They want to just understand the dynamics of this light pole. Why they're interested in light pole, which is like secondary element which we never care about? Why? Because in Kobe earthquake, so bridges were safe, but all the secondary elements, so called as this light poles or like hangers, everything got collapsed. Because of that, the traffic has been stopped, and it took for them like at least like 2 to 3 days to clear it off, to again to restart the traffic flow. Okay, so which is like unforeseen effect. Okay, so because of the earthquake, bridge is safe, but my secondary element is getting collapsed. Why? Because there is some match of frequency between with the earthquake frequency, and there is some resonance effect, and it has got collapsed. So now they want to understand the characteristics of the light pole, which is like which has crossed almost like 30-40 years, and they want to know whether the condition is good, bad, all those things. And you can see here some light poles are having some small weights with it. Okay, these are like signboards, which itself is which is like weighing like 20 to 25 kgs, which is like really creating some problem to my light pole, because it is going to change the natural frequency of it. Okay, so these are all some of the issues they try to have. So what we thought was, it is very tedious to go to each light pole, fix the sensors onto it, and do the monitoring, get the data, analyze it. It's like very tedious process. There are like thousands and thousands of light poles all over the state, and it's very difficult to do it. So what we thought was, like, if we could able to have some drones, or like if we could able to capture some images or the video of it, then I could able to analyze these things using my high performance computing analysis. Okay, so that's the reason we thought. For example, if you see, this is one frame. Let me assume this is one frame. So in this one frame, I can capture 4 light poles, so which is like quite reasonably very good for us. So similarly, you can like do in a very different angles, and all the measurements can be done. So this was the uh, expressway we targeted to implement our technique. So you can see here, so this is something like a pathway. Okay, so we are not disturbing the traffic. Traffic is, it's like going, because we are only rely upon the traffic load, which is creating my ambient environment, which is like creating my structure to vibrate. Okay, so this is my target light pole. So where you can see the video camera is fixed and laser double vibrometer is fixed to get the reference value. LDV is for the reference, and video cam is just to prove that our proposed method is working or not. We just want to analyze that. Okay. Yeah, so I'm just trying to show some selected 4 poles. Okay, so where you could able to see this is a pole, so where there is no signboard. But if you see pole 3 and pole 4, there are some signboards. So we just want to understand whether this mass is really creating some difference or not. Okay, that's the study we have conducted. So these are all some of the results, very good results we have obtained from the laser Doppler vibrometer. Okay, so just to understand what is the value behind. So roughly, if you see, the natural frequency of the light pole is in the range of 1.5 to 1.85. Okay, in this range. Okay, which is like quite good for us. Okay, it is like really matching with it. Okay, and when there is a signboard, it is like it is something like 1.6, which is like reasonably good value. So now we try to implement for the motion magnification using the computer vision technique. So where I'm just trying to show you some of the uh, frames. Let us randomly, I have picked like 1120th frame in the interval of 10. You can see that how that light pole is getting magnified. Okay, so in reality, light pole is not vibrating, but after magnifying, it is vibrating. Okay, so that's what like we are trying to say here. Okay, so these are all the responses that we have obtained, okay, for the light pole from the video machine magnification technique. So this is very much in random in nature. Vibration is so much random, and we try to implement the free decay signal from the random decrement signature. From here, again, we're trying to extract the frequency values, which is like 1.5 and 1.6, which is like it is in very good match with uh, the reference data which is obtained from the laser Doppler vibrometer. Okay, so similarly, these are all the different results that has been obtained for different set of light poles. Okay, so this is something like we try to like extract the, so it is something called as a downsampling. So I can so for the computer efficient way of utilizing it, computational efficiency, no need to use the full frame. There is something called as downsampling. You can just use wherever it is required. You can just crop that part and you can utilize that, and you can convert it, and from there you could able to extract the displacement of it. So why? Because you could able to get the clear displacement. Okay, that's the reason. So here this plot, if you see, this is like for each number of frames, how am I trying to extract that value which is displacing, okay, from one pixel to the another. Okay, so this is something like where you could able to see that how it is like trying to vibrate. Okay, so this is how the structure is trying to vibrate. So these are all some of the values, okay, the n values, which where you can compare the frequency values of both LDV and vision based, which is really good. Okay, but the disadvantage is only one thing, which is I need to know prior this value 1.5 should be the value that light pole is going to have, which is like quite tedious, which is quite drawback in this thing. For example, if you're going to change the structure, so how am I going to know the frequency of it, or at least the rough frequency of it to fix the range? Okay, so that is quite uh, like tedious. So what we did was like there is something like where we tried to develop some unsupervised learning method, so to overcome this drawback, so where I don't need to worry about my range of frequencies. Okay, so I can just take the video and I can just implement the method which we are going to propose now, just to understand what are all the modal frequencies directly. We can able to do that. That's what we're going to do. So here, more or less, like the first part is something like same. So first is the input video, we are going to do the filtering, then we are going to do the multi-scale decomposition, then phase extraction. So from here, what we are going to do is I'm not going to fix any band pass here. From phase part, I'm just going to implement principal component analysis, okay, which is like quite popular technique under the unsupervised banner. So where it is going to like help us to reduce the dimensionality of the motion matrix. That's what we have used PCA, and you can replace PCA with RPCA, non-negative matrix factorization. There are like a lot of methods like people are working on it. So once you do this PCA, you try to extract the component, okay, so which is something called as the principal component, dominating components you try to extract. So now these are all the components which is having some mixed modes. So we need to extract the mixed modes. From there, you need to extract the, I mean, you need to decompose the modes, correct? So for that, you're going to use the analytical mode decomposition. This method can be replaced with dynamic mode decomposition. There are like many methods that you can do. At the end, we try to do the RDT, which is like random decrement technique, again to separate the modal frequency and damping ratio. Okay, so here, like these are all the things. So under this PCA, so there are like particular things that we use, which is like well known to us, which is like number of principal components are calculated by computing the eigenvalue decomposition, that is EVD. Again, we try to do the single value decomposition to get the principal components. Okay, so under this PCA, there are like other two methods, which is like well known and robust methods. Okay, this is what we're going to do. This is our proposed method. So I think like this is the phase extraction. Okay, the same the expression which we saw a couple of slides back. Okay, so where you try to get the image intensity. Okay, so once you get it, then you try to go with the multi-scale and the multi-band decomposition technique, which is generally the complex terrible pyramid. Okay, so this method was proposed in 1995, which is like really robust method, which is even till date people are like researchers are using this method. So these are some of the explanation for how to use that method. So I'm not going deep into the method. Let me just, yeah. So this one small figure will help you to understand how that pyramid is going to work. So as we all know, that pyramid is something like from the uh, how it is going to like decompose from layer by layer. Okay, then how it is going to construct back. Okay, that's what it is going to do. So now if you could able to see from left to right, okay, where the pyramid is trying to construct and decompose. Okay, so H naught is something like high pass, then L naught is something like low pass. Then you under this again you fix that B naught, B1, BQ1. You just keep on trying to like do the filtering part here. Okay, so here like we are using something called as the complex Gabor filters, which are like sinusoids with the spatial frequency windowed by the Gaussian envelope. Okay, which is like quite a normal filter, which is like having a good relationship with the complex terrible pyramids. Okay, so this is what we're trying to use for the construction phase. Yeah, so now here if you see this, it's like very simple math. So this is my image intensity. So this image intensity is having some filter responses, which is having filter response. From here I'm trying to get the local amplitude and the phase part. Okay, so here once I do this Fourier transform of it, okay, so you could able to get the amplitude and phase. So the which is circled here is something called the local phase, okay, which is again given with the expression 2 pi omega naught x plus d of x comma t, which is like, which is just trying to talk about the motion matrix of that particular frame. Let us assume like that. So now this complex terrible pyramid algorithm is trying to decompose each frame, where you're trying to get the amplitude and phase. Then from phase, you're trying to again decompose, okay, to get the motion matrix. That's what we're going to do. So how we are going to do? So this phase part is having some temporal mean, so which need to be removed. Okay, that's what we're going to do. Where this is something more or less similar to our structural dynamics. Okay, it is so much analogous to the structural dynamics, where you try to do the modal superposition as a linear combination of the modal responses. So where you could able to see phi of x and q of t, where phi of x is nothing but the mode shape matrix and q of t is nothing but the modal response matrix, which is like quite known in many of the structural dynamics book. You can find this. So now similarly, I'm just going to do the same thing using this method. So where tau I of x is going to give me my mode shape, which is ith mode, and qi of t is going to give me the modal coordinate. Okay, the same thing I'm going to do. So the fixed dimension is something like much higher, okay, than the modal dimension number. That's the problem in PCA. Okay, so in 2017, okay, Professor Yang from Michigan State University, he concluded that due to the over completeness with high spatial and low modal dimensions over the complete model, the modal identification problem cannot be solved directly. That's what he concluded in this paper. So in order to solve this point, so we have used this PCA, which is like unsupervised manner, to reduce the dimension. So where this part is solved here. Okay. So now this is the PCA method, which is like well known to most of the researchers, and it is something like very direct method. So where you're trying to compute the principal components, okay, and you're trying to change the dimensions of the data, where the most of the variance part is taken care of it. Let me just go to the next slide. Yeah. So this is trying to explain how this PCA is trying to work. Okay. So let us assume you have a large data set X, capital X, with R rows. Okay. So now I'm just going to have the principal component from this large data set. Okay. So where I'm just trying to reduce the dimension of this data set by calculating the row wise mean, that is X bar, and subtracting it from the main X. Okay. So by doing this, I'm just going to get the mean value of it. Okay. Which I'm going to call that as Xj bar. So from here, I'm just trying to subtract that mean data, that is M, which is X minus X bar. Okay. This is a new value that I found using the mean value. Then I'm just trying to subtract this. So now if you could able to construct the covariance matrix out of it, you could able to easily extract the variance of this particular matrix. Okay. So this variance is nothing but the maximum variance, whatever you got, it is nothing but the first principal component. The second maximum variance value is something called the second principal component. Okay. That's what this particular expression is trying to explain us. So now you could able to fix how many components you want. But in fact, like, like next we are going to implement the eigenvalue decomposition on the singular value decomposition, which is going to tell you how many principal components are there, which is really good for us, because sometimes we don't know how many components are there. But from the video, by implementing this eigenvalue decomposition, it will explain us how many major components are existing within your particular system. Okay, that we could able to extract. Okay, so this is the very simple expression for the singular value decomposition, where you have U and V matrix, which is like trying from here, you're trying to get the singular values. Okay, so then you have like EVD, which is like eigenvalue decomposition of the covariance matrix, and you try to extract the principal active components. Okay, which is like far less than the spatial dimension of the matrix. Okay, so this is how like you try to extract. Okay, so these components is going to give you the information about the dominant frequency modes. Okay, so from here, like but the problem here is like these are like something like averaged. Sometimes you can have that mixed modes, so you need to have some other technique again over it, which is like analytical mode decomposition, to extract each modes. Okay, so that's what this slide is trying to explain, which is trying to use a very robust method, which is like a signal decomposition theorem using the Hilbert transform. So which is like quite popular. So which is also like it has been like more than 10 years, and like most of the people are using it. So even there is a development from AMD to there is something called as DMD, which is like more robust than this. Okay, we're trying to implement that as well. So where like we are just trying to have a time series signal, and you try to like separate into like different frequency component, and you're just trying to extract it. That's the story behind this mode decomposition. So you have a mixed set of modes. From the mixture of that modes, you're trying to separate those modes. So that's what you're going to do. So once you separate it, then again we are relying upon the random decrement method. So where you're going to get the free decay signal, and you're going to implement the logarithmic decrement and the modal damping ratio, which are like quite famous in the structural dynamics books. Okay, so these things like is very straightforward problem. So let me just show you the validation that we have done for the numerical model, which is something like a random 12-degree freedom system model. So where M mass matrix, stiffness matrix, and damping matrix are been like fixed as per the literature. So then, since it is like numerical model, so we took that like, okay, we'll stick with the 4 modes. Okay, then accordingly, like we try to like demonstrate how this first four modes are getting extracted from the initial responses. Okay, so after you conduct the eigenvalue decomposition, you will be getting something like this, where the indices is going to tell how many principal components can be extracted. Okay, so here we have fixed it purposefully for just to make sure EVD is working or not. These are all the principal components. So where you can see that major component is having some mixture of modes. You can see here all the modes. From here I need to extract. So I don't know which is like uh, dominating among these two or three, among these four, which is dominating. We don't know that. So we have to do it using the analytical mode decomposition. So this is the AMD method. So where you could able to see that you could able to extract the modes, okay, so cleanly, and you could able to get the power spectral density for one particular frequency, which is like really dominating that particular system. So this is something around like 5.3 hertz. And if you see the second model frequency, which is dominating at 10.10 hertz, so where you could able to cleanly extract it. So of course, here you can appreciate it is very neat figures because it's a numerical simulation. But this is going to be like so much random when it is going to come to the video measurement. Okay, so just to prove our system is working, so we are just introduce some noise to the measurement. So this is like without noise, and this is with noise. Okay, so just to perturb the system and check whether the proposed method is working or not. So these are some of the different noise signal to noise ratio has been used, and like more or less the frequency value is not changed. We are getting like very neat values. So this is the table that is trying to estimate the error. So it is just less than 1%, which is like very good results. So we tried to implement for the benchmark laboratory experiment, which was conducted by Professor Kyon in Missouri State University. So this is like single degree freedom system, and this is for the multi-degree freedom system. Okay, so where this was like quite old video, which has been like utilized for understanding whether this method is working or not. So where the video quality, if you see, it is just 480 pixels. I think nowadays we are having a smartphone which is like having like really good pixel resolution. Okay, this is like quite low quality video where the frame size is given. Similarly, the frame rate is something like just 30 fps. Okay, so similarly here, if you see, so the length of the video is just 63 seconds for multi-degree film system. So from here, like you could able to understand or extract the frequency, because this is like a simple shake table test example. So where you are extracting the vibration or the frequency value. So now this frames per second is this 30 fps is something like more or less like analogous to our Nyquist frequency, which we'll try to discuss. Okay, so uh, this is the video. I hope it is getting played. So this is something like single degree film system resonance vibration test, which is like quite famous video. So where you can see that there are like different like heights of buildings where the sweep sign test is conducted, where the frequency value is changed from 0 to certain hertz, and wherever there is a match with the input frequency and the structure's frequency, there will be a resonance effect. Okay, so let me just, you can see that like the frequency value is getting increased, and obviously for the low frequency the task structure is going to react first. Okay, that's what is happening here. So you can see that like how that structure is trying. So you can see here at 4 hertz, okay, this structure is like really having a resonance effect, and like that is its natural frequency. So now if I'm going to crop this part of the video, okay, I should like implement my technique and extract this from that video that I'm going to have 4 hertz. That's the ultimate goal of performing this test. Okay, so similarly, like you can do for the various things. Okay, so I'm just stopping here and like moving further. This is for the multi-degree frame system. So where you can like again extract the things. Okay, so let me just go here. So now I'm just trying to crop a part of it where I showed that 4 hertz. Okay, so this is the cropped frame for analysis for single degree frame system, and this is for the multi-degree frame system. So when you do the two-dimensional Fourier transform, you're going to get amplitude on the phase part. So this is how the amplitude part is going to look like. Okay, and this is the phase part which is going to contain your motion matrix. So here I'm not going to fix your bandpass filtering. I'm not going to magnify the frames. Just blindly, I'm just going to like feed into my system. Okay, so now this is the methodology which we proposed. Once we get this decomposition, then you try to remove the temporal mean, implement the motion matrix construction, then principal component analysis, then analytical mode decomposition. From there, you would be able to extract the free decay signal from where the modal components are extracted. This is the base of our algorithm. So by from the video that we have collected, okay, so by implementing eigenvalue decomposition for single degree of freedom system, there is one peak value, so which is like quite clear. For a multi degree of freedom system, there are like 1, 2, 3. So it's like 3 degree of freedom system, and we're trying to get almost like 3 good eigenvalues, which is reasonably good. So these are all the results that has been obtained by implementing the whole method which was proposed. See the modal coordinates and the PSD plot for video measurement of single degree frame system with the frequency value of 4.06 hertz. I could able to extract as 4.06 hertz, which is like very much in like agreement with the 4 hertz from the experimental thing. So where our method is really working very well. Okay, so because I'm just trying to feed the video to the methodology, I'm not feeding anything like range of the frequency or like magnifying the frames, nothing. But still, it is like helping me to get what is the frequency value. So here, like I mentioned somewhere that this video is something having 30 FPS. That means, so the camera sensor is having some frames per second. So in per second, it is going to capture 30 frames. That's the meaning for it, which is so much relation to the sampling frequency, which we generally use for the time domain signals, right? In accelerometers, particularly in accelerometer, for we always take care of the sampling frequency value. So here it is like something like similar to sampling frequency, which means if my sampling frequency is 50 hertz, the Nyquist is something like half of it, which is something like 25. Similarly here, if it is like 30 fps, this is like sampling frequency, then your Nyquist is something 15 hertz. So within 15 hertz, what are all the modes that are going to get excited that will be captured? So in this, luckily it is just 4 hertz, so we could able to extract. Suppose if my FPS is very less, then the Nyquist value will be less, then sometimes you might not extract the frequency. You should be very careful in using FPS in your camera. So we have used, like, this is something information for the CPU and the GPU that we have used. Okay, very simple, like Intel Core we have used, like 16 GB, which is like quite reasonably good system to handle. Similarly, like these are all the, this is the plot that has been obtained for the multi-degree reference system. So where like we have like very good relationship with the reference values, which is like we are having only errors of like less than 2%, which is like really good results. So we try to implement in the another like real-time videos, like full-scale video measurement. So there was no proper video that was recorded. This was something like recorded by the pedestrians. Okay, so you can see this bridge is trying to vibrate, which is like visible to us, right? So let me just play this video again. So I hope you can see this vibration with your eyes. Okay, so the story behind this bridge is something like this was opened in 2000, but the problem was there was like huge vibration which was like closed again, and there was like a lot of control devices has been like implemented just to arrest the vibration, but still there are some vibration allowed. So that like this is like in like famously it is called as like wibbly wobbly bridge in London. Even today it is like uh, in usage. Okay, so where you could able to see the vibration with your eyes. So from here, which is this, you can see this video, which is something like a pedestrian, someone like tourist has taken this video. We're just trying to extract the frequency from this random video. Okay, that's what we're going to do. So this is something like a pixel that the frames that we have just like downsampled. From here I'm just trying to get the vibration of this whatever vibration we are going to see. Okay, so if you could able to see here, I'm just showing you the amplitude part and the phase part. From here I could able to extract at least like one neat modal frequency. Why this vibration is happening? Because this bridge is trying to have a sway because of the pedestrian walking. So when the pedestrian walking frequency and the bridge frequency is going to match, then it is going to have like huge lateral movement. Okay, that's the reason this bridge is always in swaying motion. Okay, so from here like we could able to extract like 3 components. Okay, which is like more or less like having a quite good match with whatever the values that has been obtained by using some sensors. Okay, long time back. Okay, so we are trying to get some really good results, so where you could able to see the peak frequency values. Okay, similarly we have implemented the technique for one of the famous Tacoma Narrow Bridge, which is like collapsed due to the uh, uh, aerodynamic condition. Okay, there was like huge torsion, and this bridge got collapsed. So I hope you all know this thing. You could able to see when there was a wind load acting. So this aerodynamic condition was not considered in the design part. So when that wind loading frequency is matching with my bridge deck, it is just trying to show some significant amplitude vibration where your cables, everything is like vibrating, which is captured. Okay, so then it got collapsed. So if you could able to see this part, which is like having like neat clear vibration, so we're just trying to extract at what frequency this was vibrating. Okay, so that's what we're going to do. So this is something like cropped video, like random video we are taking. And if you could able to see this video, which is of really poor quality, okay, which is like random like video was taken, it is like where if you could able to see the dimension, it's just 212 pixels in height and 84 pixels in width, which is like very like low quality when comparing to the smartphone camera that we have today. Even if you see iPhone 12, you have lidar cam, so which is like much high technology has been like implemented nowadays. Okay, so this is something like a random video we have taken, and we could able to extract the value, which is again like really like matching with the values. Okay, so what I'm trying to say here is that like this hybrid method of like having this unsupervised method along with some of the system identification methods, we could able to easily extract the model parameters. So currently we are trying to replace this PCA method, so which is like sometimes like this is also creating some problems. So we're trying to replace this with the non-negative, better unsupervised learning method. So that's the current work we are doing. So where like this method can be like really useful for the real-time infrastructure performance monitoring. It can be used for the operational maintenance. For example, we all have CCTV cam, so where you could able to record the structure whenever it is required. You could maybe once in 6 months you could able to extract that video, and you can implement this method to extract the model frequency, for example, and check with the previous values. So you could able to do the assessment for say like 3 years, 5 years, and you can understand how the structure is performing due to the various loading condition and how the structure is getting deteriorated. All these conclusions can be made. Okay, so this is one of the robust method. So some of the references which we have published from the work that I have discussed today. So if you're interested, you can look into it. If not, you can just write to me. I can send these papers to you. Yeah. Yeah.
Thank
Thank
you.
you for your kind attention. Yeah.
Thank you, Dr. Saravanan. It was a very interesting concept. I must appreciate the work which you have done and the way you have delivered the lecture in a very systematic way and explaining the concept. For me, I think for many of us, it was a bit complicated, but you explained it in a very nice way. I really thank you for that. And the floor is now open for questions if there are any questions in the audience.
Yes. Uh,
And Dhawan sir.
Nice presentation, young man.
Yes, sir.
Uh,
Thank you, sir.
of course, we have been doing this SHM through piezo sensors,
Yes,
but done with a new device. Uh, Here, see, I could make out that if you can work out the natural frequency and mode shape,
yes,
and then subsequently, if there is change in frequency,
yes,
then there is possibility of some damage somewhere.
yes,
Am I
yes,
right?
yes, sir. Yes,
Now, my question to you is first, how to work out the natural frequency for the healthy structure? Uh, of course, subsequently, you can work out the way you have said through video, taking image, processing it, and you can so how to get the frequency, natural frequency in a healthy state. That is my first question.
no,
Can you just explain?
yeah, okay. So even for the healthy structures, for example, you can do the same analysis. You can just do the video of measurement of that particular structure, and you can implement this technique, and you can extract the natural frequency of it.
Yes.
Not necessarily that my structures need to be damaged. So why we are trying to look into that operational maintenance? Because for example, every time it is very tedious for us to go to the site and collect the data. So if you have some cam, it is quite easily, you just stand 50 or 100 meters away from the structure without disturbing the traffic. You can just capture the video and analyze like how my structure is performing down the lane, like let us say 5 years, 10 years, 15, 20 years. because for first 25 years or 30 years, I think most of the structures are quite good. I mean the infrastructures, large infrastructures. Only if it cross the time period of like 40 years or 50 years, there might be some deterioration which is like visible to us, and there might be some problem. Or as you know, like there are like nowadays there is an increase in the rail axial load capacity to 25 ton, for example. So now
Mm.
most of the bridges which are old, they need to be checked whether that can carry that load or not. So they are
Mhm.
trying to do the assessment of that bridges. So either way we can use this method.
No, no, my agent, all right, with respect to existing structure. Now, see, I'm a structural engineer analyzing and designing a new structure, bridge or building or any other structure. So there, see how I need to, can I validate it through structural monitoring that my analysis is okay, my design is okay. Is there any mechanism which you can suggest?
Okay. So you want to analyze during your design time.
As a designer, as a structural designer, new project,
Okay.
we're building or a bridge.
Okay.
See, I will do what are the computer analysis data, but
Okay.
to check that, validate that, that whatever analysis and design are done,
Yes.
can I validate that analysis and design through your technique?
No, actually, because like we need the real time structure. Otherwise, it's quite difficult. For doing that analysis, maybe you can do some simulation. Nowadays, we have like quite high end softwares, so where you could able to analyze your structures and check for the model frequencies and compare with whatever calculations you have obtained. That's the best way. Many are doing it.
Mm-hmm.
So
And
that's
then
just
this,
very much straightforward. So where you can
uh,
revise your design accordingly as per the IS codal provisions.
uh, and then just explain me something about the real time. Of course, you take images through video and
Yes.
then use that data in analyzing and getting the response.
Yes.
What do you mean by real time?
Or actually like real time, like we are trying to like propose it. For example, like you have a camera, so what we are thinking is that we are trying to develop an app. So you have a
Mm-hmm.
mobile and
Mm-hmm.
you try to install that app, and you open that app and you take the picture or record the video of particular structure, and on real time, let us say like maybe the time lag of like 15 seconds or 20 seconds, it is going to give you what is the natural frequency after that processing is happening. So where you could able to like move from one place to the another, again you can capture the like video wherever that is you're looking for, and again you can like extract the frequencies, something that's what like we call it as real time in this context. But generally, as you say real time, for example, if you go for the wireless sensors or like condition assessment of a bridge, you try to
Mm-hmm.
mount the sensor and you wait for like let us say 6 months or 1 year, and where the data is getting collected through IoT, you try to transfer the data to your place and you try to analyze the data, where the real time monitoring is taking place every minute, or like every day. For example, if it is temperature sensor, every day we try to monitor. So that is something called as real time. But in this
Mm-hmm.
context, I mean real time means on site immediately you could able to get the data. It's not that I need to go back, analyze the data, do the post processing, wait for some time, check it. So those things we're trying to avoid because of the available technologies.
Mm-hmm. Now, my final question is that dynamic equation
Yes.
mu double dot plus cu dot plus
Yeah.
ku is dynamic force, whatever you get.
Yes.
Here, when we analyze, we get the mass matrix, we get the
Yes.
damping matrix, we get the stiffness matrix.
Yes.
See, here, when we see that vibration or structure is more, I mean, can we use the dampers or something to control the damping?
Yeah, like as you know, like nowadays, like there are like quite a good amount of research that is happening for control, like control devices. So previously it was passive, then active, then it was like semi-active. Nowadays there is something called as real-time hybrid system. So where you
Mm.
control it. So where you have a lot of like magnetorheological dampers. So where it is trying to arrest the vibrations. So I think like for past 2 to 3 decades, like good amount of research is happening. So we can go with some high-end dampers to arrest the vibrations. That's the
Mhm.
best way, and it is going to be varied from structure to structure. So it
Mm.
depends upon the structural condition, what type of structure, how you're going to implement. For example, if you see my slides, so let me show this London Millennium Bridge.
Mhm.
So Yeah, so you can see this bridge, right? So this bridge is trying to vibrate, for example. Like this was like controlled vibration, to be honest. But when it
Mm.
was opened in 2000, there was like huge vibration. To arrest the
Mm.
vibration, they have incorporated a lot of control devices within the system. Maybe under the
Mm.
deck, if you see, there are a lot of control devices which is trying to like arrest those vibration. Still they're trying to allow that lateral sway just to like understand like how that synchronization is happening. But there are like too many control devices has been fixed under the deck to arrest, and also
Mm.
some of the cables they have like tried to fix the control devices. So it depends upon the site specific conditions on what type of like device that can be used.
Right. Thank you so much, Doctor. Please,
Thank you, sir. Thank you very much.
I'll connect you later. I would like to have your telephone number. Thank you. Thank you
Sure,
once
sir.
again. Thank you.
Thank you. Thank you, sir.
Dr. Dhawan. Shipra, you can ask your question now.
Am I audible, sir?
Yes.
Yes.
Good evening, sir. Thank you so much for your nice presentation. Actually, I'm research scholar under Professor Bhalla, and I'm really
Okay.
aspired to extend my work in machine learning. And
Oh,
I
great.
found it very useful for my research. Couple of things that I want to know is, first of all, the civil engineering work of having mass, stiffness, and damping ratio of a structure is now calculated by mathematical models. There is so where these components are actually been involved in this algorithm, or it is independent of these things, those
I think in these algorithms, it is completely independent.
completely
Yeah,
independent.
we are not taking
So,
care of all those things.
okay, sir. So sometimes our building are composite in nature, concrete and
Yes,
steel both. So when we picture or video something, so the only the structure is in the shape format, but the material specifications, it is not. It is also
correct.
independent of that.
Yes, actually, you're right. For example, let me give you a different example for this. Let us assume a bridge. So, for example, like there are like a lot of components in bridges. If you see bridge girder, bridge bearings, okay, and the bridge pier, abutment, lot of components, and all these components are getting somehow connected for the load transfer mechanism. But if you take the video of like let us assume that I'm going to take a video of abutment or the pier, I might get different frequency. If I'm going to take the video of a girder, I'm going to get the different frequency. So this is something like where local monitoring and global monitoring. So we need to be very careful in this. Again, to answer your question precisely for material thing, I think this method won't work. So we should be very careful. Like maybe we need to prune this method so that like if it is, for example, composite, as you said, there is a glass casing, there is an aluminum frame, and there is a concrete structure which is like mounted onto it. So if you're going to take the video of that cladding structures, the vibration mostly will be getting only the cladding's natural frequency.
Okay, sir. Sir,
So there you cannot expect the frequency of reinforced concrete structure, RC structure. You cannot expect.
okay, sir.
So you should be very careful, like how you're going to give input to the system.
Sir,
So
any method to predict remaining life of structures? I mean,
yeah, actually, like we are working on that topic as well. So actually, like for a remaining life structure, like most famous, as we all know, Monte Carlo simulation. So after that, there is something called as Bayesian inference. So that is like quite popular technique. You can blindly use that method. So we are trying to use that method on something called a stochastic subspace iteration (SSI). So
sir,
we are just trying to get the remaining life from there.
so are you using MATLAB or which kind of language you are using?
MATLAB. We are
MATLAB.
using MATLAB, Python.
So
Like
can I connect you more on these subjects, because I am really.
yes, yes. Sure, sure.
Thank you so much.
Yes.
So thank you, Shipra. So are there any other questions? Or else I'll ask the question because I have a couple of questions, but after everybody is done. Okay.
Hello, sir. Good evening, sir. Sir, I have a small question. Uh, Hello, ma'am. Good evening, sir.
Good evening.
Yeah,
Actually, sir, while taking the video measurement, the major problem is the storage, because the video we are taking depend upon the pixel images. So that
correct.
pixel image contains huge amount of data. So how to handle those things? And secondly, like while we're taking the measurement, that may be affected by there is some rainfall or there is some dust particles or there is
Correct.
something you can say in other US or Russia or other countries, there may be chances of fog. So like during that time, it may affect the reliability of the measurement. So how
Correct.
we can handle those things
Uh,
while we are considering the video-based measurement?
Okay, okay. So this is something like a practical way to handle. Like for example, you as you said that first question was the data thing, right? So let me answer that. So for implementing these methods, like hardly if you have 20 seconds of video, it is working for me. So there is no need to like take 24 hours data for me. You understand, right? So maybe you can collect at some intervals of time wherever there is a peak traffic time. For example, you can collect at that time, and you can always like look for that, like wherever there is some, let us assume that if there is a big truck is passing over my bridge, obviously there is a vibration that is induced. You understand? So that time can be like extracted, and that particular video which is like, let us say, which is lasting for around like 30 seconds, for example. So maybe you can add plus or plus 5 at both ends, so totally 40 seconds video can be handled. So easily like you can handle the data part. So for storage, no need to store. So why you want to store the whole data set? So if you are having a good server, of course you can store. If not, then every interval, whenever it is required in the peak time, you can record it. That's the first one. Second one, for the fog thing, yes, I think like it completely depends upon the practical situation. So, we cannot use that data, which is not reliable, right? So we need to go for the different data set. Even in the normal, like very important thing when you're going to record something, if you're going to use mobile in hand, you will have like unknown vibration because of your human error will be there. That's the reason we always try to advise to use tripod. And again, in tripod, like there will be like, for example, like I will tell you an example. So this is my tripod which is kept on the bridge deck. So we just try to record that video. Suddenly there was a car which is passing, like my tripod started vibrating, which was not expected. You understand, right? So I cannot use that data because that vibration might influence my camera measurement, right? So those are all some practical things which need to be taken care. Nowadays there is something called as anti shock shocking factors in cameras, some high end cameras. If you click it, so even for that clicking there are some sounds, some noises happening, and that handshake is there. So there you can avoid all those things. So it is just like it is something like how to say, handling the data using some for the cameras. So if you could able to sort out those things, I think the methodology will work.
Okay, sir. Thank you, sir, for the nice presentation.
Yes, yes. I hope you are doing well at IT Bombay.
Thank you, sir. Yes, sir.
Yes, good, good.
Yeah. So I have few questions, and so first is like you are saying, the camera, the tripod for the phone or the camera is to be kept on the deck. I
No, no,
shouldn't
we
be
just
on the bridge.
no, no.
Shouldn't be on the
We are just trying to. So this example, why I mentioned, because when I was capturing the video of one light pole, so we just kept on that bridge, on that road, so bridge deck.
on the bridge
But
deck.
so on the bridge, because like for example, if this is my bridge,
Yeah.
and so if this is my light pole, so I have to stand on the road, right? So this I'm just
But
laying.
yeah, I think in this example you were trying to just establish the concept. That's why you took the example of vibration of the pole. But
Yes.
otherwise, vibration of the
Otherwise,
pole as such is not a very good thing that will represent the structure's natural frequency.
exactly.
You are
Yes.
also mentioning. So these
Yes.
are the more vibrations which the structures on which you are seeing more vibrations. They are basically the secondary structures which are
Yes.
not representing the natural frequency of the actual host main structure, isn't it?
Yes.
So we
Correct.
shouldn't be actually concentrating on the vibrations of secondary structures first.
Yes. Yes.
Uh, but the second thing is, have you? There's one more technique, radar interferometry technique, which is a non-contact technique.
Yes. Yes. Yeah.
I believe that's very expensive,
Yeah.
almost
Yeah.
1 crore rupees for the
Yes.
equipment.
Yes.
So your technique is, I would say, free because it can be captured
Yes.
in the camera also,
Yes.
in your own camera, from your own camera. Uh, but another point is that instead of going into all this competition, By capturing a video and using your two methods, there is a way you keep your phone on the bridge deck and you use the accelerometer of your phone and measure the acceleration or the net
Yes.
frequency of the structure. That's also one thing which is free
Yes.
or an alternative to the proposed technique which you are suggesting here.
Okay. Uh-huh.
I mean, this is one thought, but of course, this is
Actually,
very.
I have done that experiment as well for the
Okay.
using the iPhone accelerometer.
Yeah,
So we tried to understand the condition monitoring of the railway infrastructure for
yeah,
track monitoring. So we have collected around like 160 kilometers of data we have for iPhone data. So
uh-huh.
just the iPhone accelerometer, which is like
Uh-huh.
MEM sensors. It is
Yeah,
also having a gyro and like it is really good data. So we
very good
compared that
data.
with the servo accelerometer, which is
Mhm.
like really like comparable. Like
Yes,
so,
yes.
so we have one paper on that as well.
Interesting.
Yes.
And one more thing is, like the videos which you have used right now, or maybe shown in the presentation, they are all under quite high vibrations. The structure is
Yes.
vibrating prominently, which we can see with the eyes also. But
Yes.
as such, it will not be the case when we want to measure the natural frequency of a structure, which is generally just standing. For example, a pedestrian bridge or any other bridge.
Yes.
So, will your technique be useful there as well? Or maybe what I'm asking is, what is the minimum vibration level which is required for your technique to work?
No, what I understand is that like even at that point of time, this technique is going to work because so
Okay.
when you're going to record the video, so from the I'm trying to decompose that video frames into amplitude and phase part. That
Uh,
phase part is trying to have the motion matrix.
okay.
So every structure in this world is vibrating, whether it is like seen or like not seen through our eyes, it is vibrating. So from that frames, we could able to capture that motion matrix. If you could able to get the motion matrix, this method is going to work for you.
So, can we say the sensitivity of this technique is similar to established accelerometers or any established conventional sensor? Can
Yeah.
we say that?
Yes, because like we are trying to compare with all established like methods because like we are trying to get like really good results right from the laboratory scale model which we have not conducted. We have also taken the laboratory scale model of some other universities, some real time real world scenarios like London Bridge or like thing. So
Yeah,
it is
but
like
see,
really
all the examples which you have taken, the vibration levels are quite high.
high. Yes.
So, what is worrying me is the if the level is ambient, under
Yeah.
ambient vibrations, will it work, or what level of vibrations have to be there in the structure for your system to work?
For example, like I showed you the before this part, like we showed we discussed about this light pole, right? So there we never like created any induced
Yeah,
like
but
vibration,
light
but
poles
even for
are
that it
again,
is like working.
light poles are again secondary structures. They will
Secondary
not
structures.
get
No,
moved.
no. What I'm trying to say here is that even for ambient condition it is working.
Okay,
Yeah.
then it is good. And I think in your initial slides where you compared the supervised system, supervised model before unsupervised, you were showing the validation of your supervised model.
Uh-huh.
There, the damping was not matching.
Yeah, damping was not matching. Yes, you're right.
So how, why, how, why?
Actually, like we couldn't able to extract the damping of that light pole because that study we conducted for that Kajima thing. So where that damping was not matching for us, but
Mhm.
for using this method, like somewhere damping is matching. Actually,
Okay.
even uh, today, like I'm not understanding the philosophy of damping. It's quite very strange for us to extract the damping. So only relying upon the mass matrix. See, as per the literature, it is quite simple, like relay damping, all
Yeah.
those things we can do. But when
Okay.
it comes to modeling or to the experiment, it is completely like strange. There are
Okay.
like number of like proportional damping they call non-proportional damping. So like too many things are like confusing when it comes to the real world. So honestly speaking, like I'm still like not understanding the damping philosophy. But like sometimes it matches, sometimes it don't matches. So
Okay. Okay. So
and there is no method that you can claim that like you can extract the damping ratio of or a damping value of a structure. Till now, like I'm not finding. They're just trying to compare with some reference value, some
uh-huh.
mathematical things they try to support. But there is no one robust method that we can claim that yes, you use this, you are going to get it. So
Right. Let me just say. Mhm. Yeah. Also, you was mentioning that in the light structures, in the cantilever,
Yeah,
almost the second example,
yeah,
you were not able to put sensors because they were quite heavy and they'll change the dynamic of the system.
yeah,
So piezoelectric sensors is one option which you can
yeah,
put
yeah.
for very
Yes,
lightweight. You can put for measuring the
yes,
acceleration and the natural frequency of your cantilever.
yes. But again, that is contact based.
Yeah, but for validation, I'm saying.
Validation, yes, yes,
Yeah, for validation you can use that. And
yes.
what is the minimum FPS which is required for this?
So I think like for civil engineering structures, it's like all the range is something below 15 hertz. So I think 30 FPS is more than enough for us.
30.
30. Yeah.
And what's the like tentative time of computation? For example, in this say
Uh,
London Millennium Bridge, you cropped a very small part of your
Small part. Yes,
and
yes.
to
So
reduce maybe to reduce the computational effort. So
it will be like maybe less than a minute.
uh,
Yeah.
okay. Mhm. So on the site itself, just capturing the video and then you can
Yeah,
predict.
that's the reason like I want to emphasize that real time you could able to get it. So yeah.
Okay, yeah. Thank you so much.
Yeah.
Very
Thank you.
interesting. I must say, I really appreciate. This was not known to me.
Okay.
Thank you so
Sure.
much.
Thank you. Thank you for your questions.
Professor Bhalla, would you like to conclude?
So I think we should thank Dr. JOTHI Saravanan. His lecture provided a lot of new technology to the listeners, to us, and I hope more people would be interested to take up this technology and work further. So, Dr. Jyoti, you tell us that what's the minimal requirement for a smartphone,
Yes.
which an ordinary smartphone can do all the capturing and computation for such vibrations of structures?
Yes, sir. Like because like as you see
Hmm.
the nowadays the smartphone what we are using is like
Hmm.
really quite high end technology. For
Hmm.
example, like which I mentioned, like iPhone 12, which they released, there is a lidar cam, which is
Hmm.
like it was so good to know that because lidar sensor, lidar cam is too costly, but they're trying to implement that. So
Hmm.
nowadays research is happening somewhere. They're trying to replace the drone camera with lidar camera.
Hmm.
So they're trying to customize. So that's the way we are like moving. Next year,
Hmm.
like we might have some other like
Hmm.
camera, so which is like really it will be
Hmm.
good. So this smartphone is like more than enough for us to do all these things, whatever we are showing.
Hmm. So all the competition, etc., can also be done on the smartphone
Yes, sir.
itself.
Yes.
And is there any app available as of now? Any free
No,
free
like
app
we are
available?
planning to develop that app, but we have not done that. So we have
Oh.
got some incubation center, one small project where
Hmm.
entrepreneurship and research park is trying to like fund us. So there is in
Oh.
government of Odisha, there is Niti Ayog. So I think that is there in many states.
All right.
So they're trying to register there. Yeah.
All right. Thank Dr. Sharmanan for sparing his valuable time and coming here for delivering the talk. So thank you very much, and thanks for all the audience for your time.
Thank you, sir. Thank you for the opportunity.
Thank you.
Computer vision techniques. So that can be utilized for structural health monitoring. So that's my talk.
We hold such talks every month, and if you want to join the Indian Society, Indian Structural Health Monitoring Society, you can just Google it, and you can just go to the website and fill up the application form. Thank you very much.